Now that we have our definitions, we can go back to our problem vertex cover and finally find an approximation algorithm for it. First, I want you to think about some ideas. How can we solve this problem? Doesn't have to be an approximation algorithm yet, but just any algorithm that gives us a feasible solution for vertex cover. Well, in the beginning, when we defined the problem and had our first instance, we basically already used an algorithm to get a vertex cover. Basically, we used an edge greedy. So we looked at an edge that was not covered yet and picked one of the vertices that were our incident to it and put them into the vertex cover. And we did that until all the edges were covered. Alternatively, you could also use a vertex greedy. You always pick a vertex that's incident to an edge that's not covered yet and add it to the vertex cover. The problem is that these can be arbitrarily bad. Let's look, for example, at this graph, and it could be that our greedy algorithm just picks an outside vertex repeatedly and adds them to the vertex cover, while in the optimal solution, you would only pick the middle vertex. So it could be arbitrarily bad, and this is not something that we want. And even worse, there's an even bigger question. How can we actually measure the quality? We have a problem. We don't know how to solve it optimally, so we don't know what the size of the optimal solution is. So how can we even find out how good a solution that we compute is compared to the optimum that we don't know? And here it becomes a bit tricky because actually we don't even do this. We never really compare our solution to the optimum, but we always try to find a good lower bound U and compare this to our approximate solution. So first, we have to find some way how to estimate how large opt is at least. Then we compute some solution and compare it with U. And it's easy to see if we compare our objective function with U, then this is at least as large as if we compare it to opt. So our alpha can also be estimated by this equation. That means that the task we have now is not even to find an algorithm, but first to find a good lower bound. The nice thing is that finding a lower bound also often immediately gives you a good algorithm. And that's something that we will see here now. The lower bound we get, we obtain from matchings. For those of you who don't know, if we have given a graph, then a matching is a subset of the edges such that no two edges are adjacent. So no two edges share an end vertex. Or alternatively, you pick at most one edge for every vertex. And a matching is maximal if you cannot add any other edge to it. Now, in this is a maximal matching because every edge that's unpicked already contains one of the vertices that are in the matching. But how does that help us? With the matching, we want to find a lower bound for the optimum. Now you can think again, how can I get a lower bound for the optimum of the vertex cover from a maximum matching? Actually, the maximal matching itself gives us a lower bound. And that is quite easy to see. We take this maximum matching and we just pick one vertex for every matching edge. Now this is the vertex cover of the matching itself. For every edge we have picked one vertex. And the matching is a subgraph of our input graph. So the size of this vertex cover cannot be larger than the size of a vertex cover of the whole graph. So the size of our matching is a lower bound for the optimum. But is that maybe already our solution? Is this also an upper bound? Maybe the size of a maximal matching is exactly the size of a minimal vertex cover. Well, since I already told you in the beginning that finding a minimal vertex cover is NP hard, and finding a maximal matching is polynomially solvable, this is obviously not the case. But can you find an example where the size of a maximal matching is really smaller than the size of a minimum vertex cover? Let's have a look at this very small example. This is just a cycle of 5 vertices and 5 edges. If I pick a maximum matching, then it contains exactly 2 edges. But if I want to pick a vertex cover, then I have to take 3 vertices, because even if I just take 2 vertices incident to the matchings, one of these 5 edges will not be covered. So here, the size of the minimum vertex cover is really higher than the size of the matching. So this is not the correct answer. However, there is a very elegant solution that gives us a feasible vertex cover. And that is just take the maximum matching and for each matching edge, pick both vertices. So for this matching edge, pick this and this vertex. For this one, pick this and this. And this actually gives us a vertex cover of the whole edge set. Why is that the case? Can you prove that this is really a vertex cover? For that, assume that there is some edge that is not covered by our vertex cover. By the choice, that means that both its end vertices are not incident to a matching edge, but then we can just extend the matching by adding this edge to it, which means that the matching was not maximal to begin with, so we have a contradiction. That means that we now have an algorithm. We compute a maximal matching, we take the both end vertices of every matching edge and put it into the vertex cover. And the size of this vertex cover is twice the size of the maximum matching. And since we know that the optimal solution is at least as large as the maximum matching, this algorithm gives us a solution that's at most twice as large as the optimum. So we have our first factor 2 approximation algorithm. Let's try to formulate this algorithm. We have an algorithm vertex cover that starts with an empty edge set that will contain our matching. For every edge in the graph, if it is not adjacent to an edge in our matching, then we just add it to the matching. And now we have computed some maximum matching M. And for every edge in this maximum matching, we return both end vertices, and we're done. And this is a factor 2 approximation algorithm for vertex cover. The big question is this the best we can do? Are there better approximation algorithms? The answer is yes, but not really. There is an approximation algorithm that has factor 2 minus theta of 1 over square root log n. So this is technically smaller than 2, but not asymptotically, because when n gets close to infinite, this gets close to 0, and then you arrive at a 2. So this is basically the best approximation algorithm that we know for vertex cover. And it is so simple. On the other hand, people already looked at the question, how low can it get in theory? So there are two directions that you can go. One is find an algorithm that improves the approximation factor. And the other direction is show that there is some constant where you cannot get better than this. Since it's NP hard, if we assume that P is not NP, we know that there is no one approximation factor. But it has already been shown that you cannot even approximate it with a factor 1.3606 unless P equals NP. And then there's also the so-called unique game conjecture. There are a lot of proofs that say some problem cannot be approximated with a factor less than something if the unique game conjecture holds. We will not cover the unique game conjecture in this lecture. You can read about it online. And the thing is that some people believe it's true, some people don't. It's maybe about 50-50, so take this with a grain of salt. But if this very big conjecture holds, then this is really the best thing you can do. You cannot get any constant better than 2. This is not a constant. This is 2 minus something very small, some very small function. But there is no constant better than 2 with which you can approximate vertex cover if this conjecture holds. That's it for the first lecture. Thank you all for listening. I hope that you stay with me until next week and that you will also look at the next videos and that you will participate in the tutorials. Thank you.